Transform your perspective on 3D space. Join us as we break down rotation matrices and their incredible role in both theory and real-world applications. In problem A.14, we're using the standard bases I hat, j hat, k hat, which are the traditional x, y, and z directions, for vectors in 3 dimensions. In part A, construct the matrix representing a rotation through angle theta counterclockwise, looking down the axis towards the origin about the z-axis. Part B, construct the matrix representing a rotation by 120 degrees counterclockwise, looking down the axis about an axis through the point 1, 1, 1. Ooh, this one's a little mind-bending. In part C, construct the matrix representing reflection through the xy plane. And finally, but certainly not least, check that all these matrices are orthogonal and calculate their determinants. Very, very important question. So because of its importance, let's consider this. Rotations can be effectively represented using transformation matrices based on direction cosines. This approach, rooted in classical mechanics, offers a more intuitive physical understanding of the concept. Denote the angular separation by the parentheses xi prime and xj. Here we see all the separation angles. And in this, what we can say is that to obtain a point in the rotated bases, or the rotated bases, we apply the transformation matrix to the original point, which can be represented formulaically as matrix multiplication. And this is how we deal with rotations in 3D space within the scope of classical mechanics. If I want a primed axis coordinate, I create the direction cosine matrix, multiply it by the previous point, which is just lambda in this context multiplied by the point. Now, a couple notes on this that'll come back later. In the classical mechanics world, at least in the book I'm referencing, they put their prime axes as rows, whereas a lot of books, this quantum mechanics book included, puts theirs as columns. All that is a transpose difference, but since we're proving that these are orthogonal, we're pretty much good to go anyways in a lot of ways, but definitely be aware of the context for which you're making the primed axes. So in part A, in this transformation, the x and y axes correspond to a standard 2D graph. Okay, so we have x horizontal, y vertical, and z coming out of the board, or perpendicular to the page. And then a counterclockwise rotation indicated with the black arrows by some amount theta can be seen here, and we can visualize the rotation. So all we're doing is keeping z stable, rotating the x and y. And a couple of things to note here is that our original xy were at 90 degrees, and so are the y prime and x prime. They're at 90 degrees. Now this will help us in the direction cosines. So let's take this part by part. So if we're looking at the angle between x prime and x, which is theta right here, that's just a theta difference, right? We don't know what theta is, but we know that it's some finite amount, assumably. So all we can say is that the direction, the angular separation between x and x prime is cosine theta, so that's the amount that we have overlap, so to speak. Now, if we look at the angle between x prime and y, the directional cosine here, well, let's throw back to the diagram. We know here that there's 90 degrees in order to be orthogonal bases in x, y, and z. So if this is 90 degrees, then we know that this angle, phi per se, is equal to 90 minus theta. And that's what we see inputted here. Okay, because we're looking at x prime and y. So it has to be 90 minus theta. Then when you apply the sum difference identity, all you get is a sine theta. So pretty much simplifying down to results that we should be familiar with, but at least we can prove it now. Finally, for the x prime axis, we see that the x prime is still perpendicular to z prime and z itself. So that's 90 degrees, and that gives us a zero overlap, so we don't have to worry about anything moving there. Moving on to the y primes, the y prime and x separation, well, we have theta here and this 90 degree here, so we have to add them. Upon adding them, the sum difference identity brings us to a negative sign. So that's where we see our familiar rotations. Clearly, the y prime and y, that's just separated by an angle theta. Y prime and z, that is the green solid axis, that's still at 90 degrees to z, so we're good. And then we kind of work backwards. We see that z prime and x, the transpose of this, so to speak, is 90 degrees, so we're good there. Z prime and y, the opposite of this, transpose, so to speak, gives us a 90 degrees, so we're good there, since z prime is equal to z. And then z prime and z, well, they overlap completely, so the angular separation is 0. Therefore, we have a component of 1 there. And that just represents that the rotation does not affect the z-axis, which is pretty cool to see coming in a matrix form. So to put this all together into our rotation matrix, we have the x prime x, x prime y, x prime z, y prime x, y prime y, y prime z, z prime x, z prime y, and z prime z. So we see that this is our rotation matrix. Now, geometrically, if we look at this graph again, we can see that this can also be looked at via just maneuvering with vectors in space. Meaning that if we look at I prime here, which is now the x prime because we're just focused on the direction only, we see that we have some amount going in the positive x direction of the original bases. That some amount, since the angle is touching that axis, is cosine, because cosine was adjacent over hypotenuse, so we're just looking at the adjacent side. Similarly, we also know that x prime is now something vertical, which is positive in the original y bases, so we have some amount sine theta in the y direction. Now, if we look at the y prime, which is j hat prime, we see that we're pointing to the left now, which is in the negative original x direction. So that amount is negative sine theta. And we're also still pointing up in the original y direction, so that's some amount cosine theta. Meanwhile, we have that z is overlapped with z, so k a hat prime is equal to k hat, and we're good. That being said, we see that the I prime, this thing, goes to this row. Okay, again, most books put these as columns, and we'll see that reflected either way. And then we see that j hat prime goes to this row here, and we see that we get the same result either way. So we are definitely good to go on this. We just have to pay attention to, is it a row construction or column construction? That's going to be a big theme in all of these texts. All right, so if we're staring down the axis from a point at 1, 1, 1, as we kind of see traced out in this box, although it could be any axis in 3D space with coordinates x, y, z, or the x hat, y hat, z hat direction, about an amount theta, right? So this is a fundamental challenge to kind of get it into our brains pictorially. And if you kind of dig into this, it kind of reminds me of quaternions and how they kind of naturally represent rotations as the kind of extension of the complex plane. Every time you multiply by I, you get a 90-degree rotation. Something similar works up with quaternions. So graphically, we see that this is kind of what's going on. Now here, the axis is the vector from the origin to the point 1, 1, 1. And theta is a rotation of 120 degrees. But what is special about 120 degrees? Well, that's a third of a circular turn. So if we have 3 axes and we turn the system by 1/3 of a circle, all that does is take the x-axis and now puts a prime on the y from this point of view. And then from the y goes to the z from this point of view, and z to the x. So we see our primes just overlap on varying dimensions or varying of the original bases, so we're good. But the direction cosines here are going to be really easy to calculate because of this quote overlap that we see from this point of view of 1, 1, 1. So if we're looking for the difference between x prime and x, well, x is here, x prime's here, so the actual difference from the two vector viewpoints here, once we rotate them, is just 90 degrees, because x prime is now on top of y, so that makes sense. What about x prime and y? Well, we see that x prime is now on top of the original y, so their angle separation is 0, and hence cosine is 1. What about x prime and z? Well, clearly x prime is to the z-axis is 90 degrees because our original set was orthonormal, or orthogonal at least. We could have some length. So therefore, 90 degrees gives us cosine 0. And if we run through the y prime and x, y prime's here, x is there, 90 degrees. Y prime and y, that's still 90 degrees. Then y prime and z, now we see that y prime is on top of z, so the angle is 0, and we get a cosine value of 1. Z prime and x, well, we see that z prime lies on top of x, so we get a cosine value of 1. Z prime and y, z prime here, y here, this is still 90 degrees. And finally, z prime and z, we see that they lay at 90 degrees, so we get a whole lot of zeros, which makes our lives easy, but we see that all we did was replace one set of axes with another. So putting our x primes here, we had 0, 1, 0, 0, 0, 1, 1, 0, 0. So what this tells us is that the x prime is now in the position of y, the y prime is now in the position of z, and the z prime is now in the position of x. Pretty darn cool way of representing this. So let's take a look at this like we did last time, where we just use a graphical intuition. We see that our I hat prime now plants itself on y, so that's j hat. J hat prime now plants itself on z, so k hat. And z hat prime, or k hat prime, z prime plants itself on x, so it now becomes x, or the I hat. So I prime, j hat prime goes to z, k hat prime goes to x, and we're good to go. Either way, you obtain the same results. Now that we've kind of seen how this thing runs through a couple times, a reflection through the xy plane simply inverts the z-axis. So what we see here is that the only thing that changes here is going to be the z and z prime. X prime with everything else, x prime lies on top of x, so we're 0, 90 degrees, so we got that covered. Our y's, well, y prime lies on top of y, so the separation is 0, so we stay 1 there. And now we just have to be careful with the z prime and z because they're inverted, so z prime now lays on top of the negative z-axis, so that's a separation of 180 degrees. Cosine of 180 gives us -1. So using the separation angles like this makes it really intuitive, I feel, based on where the axes line up with comparison to the others. So that's very, very helpful for us. So now, summarizing this, x stays on top of x, y stays on top of y, z goes to the -z, and so that's represented in this transformation matrix. So geometrically, we have the same thing, I hat, I prime goes to x prime goes to x, y prime goes to y, z prime goes to -z, so we're good. Either way, you're going to obtain the same result. Now, again, I'm going to put this in writing. This quick note, this construction puts the prime axes into row vectors, x prime, y prime, z prime. Now, based on what another text put them as column vectors, where this would be x prime, y prime, z prime. Okay, so based on what you need, simply take the transpose and you're good to go. For completeness then, here are the transformation matrix in both constructions. So we see that for just an arbitrary rotation about the z-axis, we see that we have the one we found with direction cosines that puts them as rows, but here is the transpose of that which puts them as columns. And this one is probably the most commonly seen in this formalism, where we have the column construction. So if you look up rotation matrix about z, this is something that you're going to find more frequently. Note that the geometric underpinning of this is the same. We went up some direction in the from the x-axis to the x prime axis. So we had some amount sine there, which says that cosine has to be the direction left over in the original x direction. So we're good there. The geometric underpinning is still the same. How we want to construct them just changes up whether we take a transpose or not. So this one clearly 0 on the main diagonal, awesome, but these two ones go down here, this one goes up there. This last one doesn't matter at all because everything lies on the main diagonal. So now we get to move into the concept of the orthogonality again. So to check for the orthogonality of matrices, we need to see if the following conditions hold. Now, to be orthogonal, we're told that the transpose equals the inverse. And if this is true, then if I multiply this transpose by the matrix itself, knowing that the transpose is the inverse, I should get out the identity matrix. Now, we need to show that this holds in order to conclude that this is true. As a result, when we take our matrices that we had, we see that we had lambda A and then lambda A or transpose, but that was this lambda A and TA that we found on the summary page. So we had to use both constructions anyways, which is pretty darn cool. And now that we see that we have these color coded up, sines and cosines being multiplied together with the negative sign, most of them are going to cancel away, but especially with the zeros here. But in the cases that they don't, like this row to this column, we are going to have the Pythagorean identity come through and hold us down. So this row to this column, for example, we had cosine times cosine, that's the cosine squared. Sine times sine gives us sine. And we had 0 times 0, that's just 0, so why include it here? Although in the PDF for the patrons, I did the full matrix multiplication, so you could check your work. This row to this column, we see that we just get cosine, negative sine, sine, cosine. They cancel out, easy enough. And then we get 0 here because every component has a 0. Run this through. We see that this to this, the negatives cancel, so we end up with a positive sine squared plus cosine squared. And then finally, this row to this column, which is the only other non-zero, we have a 1 squared. So Pythagorean theorem comes through and we have cosine squared plus sine squared gives us 1, 1, and 1 on the main diagonal. Get rid of the colors. Now that we're done with the algebra, we see that we have the identity matrix here. So we can say that that's equal to I, and we do satisfy the condition needed in order to make sure that these matrices are orthogonal. Pretty darn cool. Of course, testing these for the other ones, a bunch of zeros and ones. It looks like we're looking at binary code once again. But that being said, the matrix multiplication is pretty quick. Row to column, lots of zeros. This one to this one, we only have one non-zero element. And then you see, if you want to take the time to look at this, we have a lot of zeros that cancel out and a lot of zeros times ones that cancel out. So simplifying that down, we see that we only have something when we have a main diagonal element. This row to this column, this row to this column, this row to this column. Those are the only elements that have no non-zero overlap. So we see 0 plus 0 everywhere. Let the color code take you through and guide you. We see that the ones on the main diagonal, since they're all squared, go to 1. We replenish and get the identity matrix, so we're good to go for this one as well. This one is arguably the easiest one to multiply because it's just two identity matrices with the caveat of this negative here, but we'll see that that inevitably cancels out. So we see we have ones here, negative 1 times negative 1. Everything else has a 0 component. 0, 0, 0, 0, 0, 0, 0, whole lot of zeros everywhere else. So in typical fashion, we see that we have 1 squared, negative 1 squared. Guess what? That goes to 1. So take away the colors now. We see we re-implemented found the identity matrix. So once again, we're good to go. And all three of these are orthogonal as you would have hoped they would be. Finally, now we have to get on to determinants. And if we didn't have enough practice with this earlier, now we definitely do. As a result, we've been used to expanding about rows, so now I'm going to do all columns. The reason why is because we have columns of 2 zeros, and in a 3x3, that makes us have to evaluate only one minor or subdeterminant, which we'll see now. So taking the determinant of our rotation matrix, again in the lambda form, we see that expanding about this column, we have 0, 0 as our cofactor numbers and 1. So we're going to use plus, minus, plus as our cofactor signs. So we have our plus, minus, plus structure. Good to go. Then our subdeterminants. Well, we're going to have to cross out this column and this row, leaving us with these 4 elements. That's what we see here. Now, when we get to this element, we have to cross this row out, this column out. We have cosine, sine, 0, 0, 0, 0. Good to go. Lastly, get rid of this row, get rid of this column. We have nothing but sine and cosine inside, which is perfect. As you see, because our minor determinants are being multiplied by 0, we don't have to evaluate them. That leaves us with plus 1 here. Bring cosine times cosine, that's what we see here, minus sine times negative sine. The negative signs cancel, and then we get cosine squared plus sine squared, gives us 1 times 1, gives us 1. So we get a nice result. Following the same concepts here for the second rotation matrix in the lambda form, where x went to y, y went to z, z went to x. We see that we have a column. All columns and all rows have 2 zeros. So we'll go about the middle one this time just for practice. And as we see, we have a 0, 0 there and 1 there. So our signs for the middle column are negative plus negative. Put this in, we see that we have our determinant now. Negative plus negative, 0, 0. Cancel out those subdeterminants. And now we're left with, just to reiterate, cross this row out. Let me actually just write it in. Cross this row out, cross that column out, and now we see we have 0, 1, 0, 1, 1, 0, 1, 0, and now we just have one simple calculation left. 0 times 0, 1 times 1, take the difference, we see we have that, and then we have the 2 negatives cancel, so we get 1, so that's pretty good, and we'll talk about more about why that's important. Finally then, we have our third rotation matrix, which again should be probably one of the easiest because of all the zeros and ones. That being said, we'll go about the first column now. So we have plus, minus, plus, plus, minus, plus. Our first number of expansion is 1, 0, 1, 1, 0, 0, or 1, 0, 0, 1, 0, 0. Cross out. We have this subdeterminant, which is what we see here, 0, 0, 0, negative 1, what we see here. And then we have this and this crossed out, so we have all 4 of those, what we see there. Nonetheless, because we have a 0 multiplied, those 2 subdeterminants go away, and all we have left is this 1 times this, run it through, 1 times negative 1, right there, minus 0 times 0, right there, zeros cancel, so we're good. And then we have a positive 1 times a negative 1, which leaves us with an overall negative 1. So, based on what we know about determinants and their geometric quantities, this demonstrates that simple rotations preserve the scale of the bases, while inversion scale it by a factor of negative 1, which makes sense. If I'm going in the other direction, my scale is now inverted. Okay, so this all aligns with our intuitive understanding of these transformations. Very, very cool to see, and if you haven't seen it, there's a lot of videos out there that talk about why the determinant matters, what it means geometrically. If we're in 2D, that represents an area. If we're in 3D, that represents a volume. If you've taken multivariable calculus, you've definitely seen this with the triple product rule giving you the volume of a parallel pipette, things like that. Very, very useful to us outside of just linear algebra, but they also tell us about the system dynamics in a sense, so very important tools to get under our belts. So that was a fun, insightful video, and I like the geometry coming back, so it's not just, crazy mathematics and weird looking hieroglyphs. That being said, if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I also just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, especially with your feedback, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting this channel and joining our Patreon community, You can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. More importantly, how they connect. As always, thank you for watching, and until next time, stay curious.